University of Central Florida, deriving muscle pathway of the gastrocnemius using motion capture and ultrasound for musculoskeletal modeling. Eric, take it away.
I think Natalie has my slides. Perfect. Okay, so yes, hi. As you already know, my name is Irani, and today I'll be presenting our new methodology for deriving the muscle pathway of the gastric using motion capture, ultrasound, and musculoskeletal modeling. And I have no conflicts of interest to disclose. Next slide, please. Should I just say like next, or is there? I don't see a open. Technical. Okay.
I'm sorry, I lost connectivity briefly. Can you guys see the slides?
Yes.
Am I on the right slide, Eric?
Yes, ma'am.
Okay.
All right, cool. So yes, as we know, impaired individuals benefit from gait analysis in order to better understand their muscle contributions during gait. So we use this on individuals who have cerebral palsy or have suffered from a stroke to better understand how they are walking. And this gait analysis is dependent on musculoskeletal modeling and generic musculoskeletal models, which use different muscle geometries to represent those humans in our simulations. But these muscle geometries in particular are extremely important because if the muscle geometry is meant to represent our participants are inaccurate, then our calculations will be inaccurate. And so this can affect things such as the force length curve, force velocity curve, and the moment arm. And so this calls into question, are these generic models good representations of those impaired individuals with altered muscle geometries? Next. So one of the generic models that's commonly used is the Thaling model. And this is a model that's based off of the analysis of 5 cadaver subjects. Next. And then another more recent of these models is the cadaver model, which was then based off of 21 cadavers, as well as the MRI image analysis of 24 young and healthy adults. Next. And so what I'd like to point out here is just the differences between the muscle geometries in between these two models. So you can see here, these are both scaled to represent the same subject, and yet they have obviously apparent differences in their muscle geometries. And so this really emphasizes, how do we know whether or not one muscle geometry versus another is a better representation of these subjects, and are these good simulations in order to represent these people? Next. So this brought us to our objective. We wanted to evaluate our subject's muscle pathway. In order to do this, we needed to develop a new method. Next. So the reason we needed to develop a new method is because methods like MRI are extremely time consuming and they're cost prohibitive. And then in particular, when it comes to cadaver analysis, you can't really do in vivo analysis of subjects using that. Next. So once we determined our new method, however, we really wanted to focus on finding which model is a good representation of our subject's specific pathway that we got from our experiments. Next. So in order to do this, first we began by creating a scale model. Next. We placed a series of both arbitrary markers and markers on different bony landmarks on our participants, and then we asked them to perform a series of leg movements. Next. Next again. And from this, we were able to determine the functional joint center of their hip. Next. Next again. And using this functional joint center, as well as the positions of their different bony landmarks, we were able to create a scaled model that directly fits our participant. And this is extremely important because we base our bone geometries off these different functional joint centers as well as marker placements. And that affects our insertion and origin points for our muscles, which we still continue to use in our muscle pathway development for this experiment. Next. So then after we had our scaled model, we then began to collect our data. So we began by having our subject lie in a relaxed resting position with their gastric exposed next, and we dragged our ultrasound probe distally across the muscle belly of the gastric. Next, while we were doing this, we captured a series of cross-sectional images of our subject's gastrocnemius. Next. And these images were then put into our images analysis software, ImageJ, next, in order to locate the body of the gastrocnemius, next. And from this body, we were then able to determine the position of the centroid of the muscle. So we wanted to find the centroid of the muscle because we believe this represents the line of action that the muscle applies its force through at this specific location on the gastric. Next. This was done at a series of both knee and ankle angles because we really wanted to look at the biarticular nature of the gastrocnemius and how that affected its muscle pathway. Next. While this was going on, you're gonna have to click the video. While this was going on, we collected motion capture data in order to account for the positioning of our subject's leg, as well as to locate the position of the ultrasound probe throughout the experiment. Next. Or yeah, X again, I guess you don't have to click it. Yeah, okay, so we combined these two series of coordinates in order to generate a series of points which represent the 3D location of the muscle center line points. These points were then used to create a third order polynomial that represents the pathway. And looking at our first participant, we noticed something that was a bit odd. Being that their muscle pathway was more closely resembled that of the thaline rather than the Rajagopal model. And this kind of spurred us on because originally we had thought, okay, if it's a more recent model, it'll be a better fit for our subject. But this kind of spoke to the contrary. So this sort of probed us, and this is why we wanted to go further with the study. Next.
1 minute left.
And so in our next trials, we tested a bunch of different angles, and we again got good R-squared correlation. So we know that these pathways are good representations of the data that we collected, and we could, especially from these graphs, see how that muscle pathway sort of dipped and became tight with the different flexion of both the knee and the ankle. Next. And then going on to compare those pathways we collected, we can see that with the solid line being our experimental data, that this participant 2 is actually more closely resembled the pathways of the Rajagopal model rather than the thaline model. Next. And this is again seen when looking through the coronal view. So we can see this is both. This is a fully the 3-dimensional similarity is much more towards that of the Rajagopal for our second participant. Next. And so overall, the main thing that we seem to look at was that when we're looking at these healthy individuals, we can see that they are more preferential to one or the other generic models when it came to their muscle geometries. And so this made us think, well, if healthy individuals are more similar or dissimilar to one of these models, how similar or dissimilar are those with altered muscle geometries? Are they even farther or closer to one of these generic models? And so this is our reasoning behind finding the muscle pathway and better understanding what our participants' actual muscle geometries are, because we need to know which one of our generic models is the best selection to represent them. Another thing that we found going through the study was that possible pressure from the probe might slightly deform the cross-sectional images that we're getting. And so this could cause some alterations in our overall pathways, but that's something that we're gonna adjust for going forward. And then along with going forward, we wanna do some future work looking at some MRI data in order to collect similar centerline data, just as something to compare with, something to look at to validate our data with. And then we also want to compare the muscle pathways when the gastric is active versus when the gastric is inactive, just to see how that also changes the muscle. So thank you for your time, and please continue with your questions.